Good afternoon, everybody. This is Alicia Carriquiri at CSAFE, speaking to you from Iowa State. We have a webinar coming up, but before we go there, let me make a couple of announcements. After this one, we're going to have another center-wide webinar on March 1st at 11 a.m. Central Time. And that's going to be a panel discussion on the likelihood ratio with NIST researchers and the CSAFE team. And in particular, we're going to be focusing on a recent paper that was authored by Steve Lund and Harry Iyer that has given rise to a whole lot of discussion. So that's going to be a 75-minute webinar. We hope that there will be lots of people with lots of questions, and we're looking forward to that. Also, I wanted to announce our all-hands meeting that's going to take place in Ames on June 11 to 13. And we are thinking about dedicating part of that meeting to be a continuation of the discussion that started last week in Washington, actually 2 weeks ago, around the topic of error rates and how to define them, how to measure them in forensic sciences. That turned out to be a wonderful workshop, and we want to continue that discussion. As always, please follow us on Twitter. I feel like a television announcer. Okay, and so today's presentation is by Xiao Tai from our partner institution, Carnegie Mellon, and she's going to talk to us about breechface mark analysis, and in particular, the comparison of 2D images with 3D images. And I am going to let the control go to Xiao. We'll stop sharing so that Xiao can start.
Okay, thanks, Alicia. Just give me a second. Okay, can you guys see? Is it full screen? Alicia?
Mic in.
Better try harder.
Oh, I guess they turned off the microphone.
Is yours on?
Mine, I think, is fine.
We see you and hear you. You're full screen.
Oh, perfect. Okay. Okay, thank you. Okay, thanks everyone for joining this webinar, and thanks to Sarah and the people at Iowa State for organizing it. So I'm going to be talking about comparing breechface marks, in particular the comparison between 2D and 3D data. So 3D is newer work that we've been doing, and I'm going to compare this to previous work that we've done on 2D. So many of you might have heard my earlier 2D talks, so there's going to be some repetition, but I'll try to keep this to a minimum. For the benefit of people who might be new to this, I'll just start with the background and motivation. I won't go into that in many details, and I won't be talking about, say, like PCAST or the literature and so forth, but if people have questions, please feel free to ask me. So I'll talk about the data and the differences between 2D and 3D, followed by the methodology that we're using for 3D data. And then I'll talk about the results for 3D and how this compares to 2D, and I'll end with future work. So this is an animation of a gun being fired. We're gonna look at the yellow things, which are the cartridges. So just focus on the one that's on the top. So you'll notice that the cartridge is pressing against this blue part of the gun, known as the breech block. So it's then hit by this long piece called the firing pin, which causes it to split into two components: the bullet that goes out the barrel and the cartridge case that's ejected from the side. So this process leaves at least two types of marks on the bottom surface of the cartridge case. The first is the firing pin impression, which is caused by the firing pin hitting the cartridge. So this would look like a big depression. And then we have the breech face marks. These are caused by the breech block pressing against the cartridge. So the breech block is made of a harder material compared to the bottom surface, the primer surface of the cartridge. And so imperfections on the breech block are impressed onto the cartridge case. So you can see the marks more clearly in the next couple of images. So this is just a picture of the cartridge case. The various parts are labeled. So we have the head stamp. So this is the numbers and letters on the bronze area. So these are stamped by the manufacturer just to say what type of cartridge it is. Then we have the primer area that's circled in blue. So this is the part where the firing pin hits. So you can see the firing pin impression, which is the big hole. So this is the first type of image that we have been working with. These are 2D images. They're taken using a reflectance microscope. So what this is the microscope just magnifies the image and then takes sort of like a picture of it. So it measures the reflectance of light from the different parts of the cartridge case. So you can see the various components. The head stamp is you can see some outlines of the numbers and letters on the outer parts of the image that corresponds to the head stamp. And then the black ring is just sort of a gap between the bronze area and the silver area. And then the primer circle with the outer blue circle, and the smaller blue circle is the firing pin impression. So what we're interested in this part in this work is just the breech face marks, which are the marks in the area between the two circles. So again, these marks are caused by the breech block pressing against the cartridge. So this is the second type of image. So these are 3D topographies. They're taken using typically confocal microscopes. So instead of measuring the reflectance of light, here we're measuring the depth of the surface. So the values that we would get would be in microns. So that's 10 to the -6 meters. So for this particular image, we get values between 0 and 250 microns. And I plotted it here as a grayscale. So the dark values would be small values of depth, meaning shallow areas, while the light values are high values of depth, meaning deep areas. So in this particular image, you can see that the primer area where the breech face marks are shallower. So you get shallower. So you get darker values, and then the firing pin impression has lighter values, so it's deeper, which makes sense. So again, so these are the breech face marks that I've marked out. So the important thing is that each gun is thought to produce unique marks. So this means that cartridge cases fired from the same gun are expected to have marks that are more similar compared to those coming from a different gun. So this is useful because when a cartridge case is retrieved from a crime scene, yeah, what's your question?
Given that you're measuring depth here,
yeah,
how critical is it that the case is inserted into the microscope in a particular way?
So later when I talk about the pre-processing, I'll talk about like one or two steps where you can correct for how it's inserted. Well, do you want me to explain it now? Well, so basically,
if you're going to
okay.
get to it later.
Okay, yeah. Well, I'll just be talking about if it's inserted with like a tilt, then we can correct for that. I'm not sure if you're thinking about any other types of ways that. Okay.
We cannot hear the questions or the answers.
Oh, sorry. So the question was if there was any type of correction that we made for how the cartridge case was inserted into the microscope during the imaging process. Alicia? Did you hear that?
What? Yeah, you hear the question, what the answer?
Oh, so the answer was that we can correct for tilt, and I'll talk about that later.
This is Sue Ballou, and my question just on that same point is,
Okay.
don't you follow protocol?
Me? Well, so I'm not taking my own images so this analysis that I'm doing right now is using this database, and I'll talk about that in a second as well. But I'm not collecting my own images yet.
Correct, but my point is, when images are taken, you follow a protocol, so they're all taken at the same point on the stage.
Okay.
That's important.
Okay. Yeah. Roy says that's important. Okay. Should I move on? Okay. Well, I'm gonna move on. So, oh, anyway, so I was saying why this is important is that when a cartridge case is collected from a crime scene, it's often compared to cartridge cases that were collected from previous crime scenes to see if any of them were fired from the same gun. And if they were, then evidence from different crime scenes and information from different cases can be combined, and this helps to generate investigative leads. So another situation where this might be useful is if we have a suspect and the suspect's gun. We can do test fires from the suspect's gun to try and figure out if a retrieved cartridge case could have come from that suspect's gun. So in such situations, finding similar marks might implicate the suspect. So what we're trying to do in this work is to do this matching process automatically. So given a new image and some database of images, there's two questions that we try to answer. The first is, how similar is the new image to images in the database? So typically we would use some kind of a similarity metric and come up with a set of scores. The problem with this is that the scores in itself might not be very meaningful or interpretable. For example, if you change some of the pre-processing steps, these might change all of the scores. Also, if we use a different score, then the new score might mean a different thing. So the second question tries to address this by giving more meaning to the score. So we ask the question, what is the probability of obtaining this result by chance? In particular, we're interested in the probability of getting a higher similarity if the two images are not a match. So, but for today's talk, I'm just gonna focus on the first question. So I'm gonna be mainly talking about similarity scores. So the data that we're using comes from NIST database. So there's over 800 images of known origin. Known origin means we know exactly which firearm and which cartridge case produce each of these images, and they're organized by study. So this means, so organized by study means there's various groups in the firearms community that conduct various studies to investigate different hypotheses, and in the process they might come up with, they might have some collection of cartridge cases. They pass these collections to NIST, and NIST images it and adds it to this database. So I've listed some of the, yeah.
Is the number 800 enough to do what you need to do here, given what is likely to be the very small variation?
Well, I mean, of course, the more the better.
Sure.
But
we're talking about sample size here.
right.
You can carry on, right? But that's an important issue too.
Yeah.
Right. And it might make sense, given that we're broadcasting, to have Xiao go through.
I asked Bill if I could ask, and he said, okay.
Okay. We just gotta learn how to just get not able to follow what's happening.
Sorry, the question was if 800 images was enough to do what we're trying to do, and the answer is, of course, the more data we have, the better. Okay, all right, so. Anyway. Okay, so I've listed some types of, some of the different types of studies that we have in this database. The first type is consecutively manufactured. what this refers to is consecutively manufactured pistol slides, and so a pistol slide is the top part of the firearm that was moving when it was fired, and the breech block is part of the pistol slide, so it's responsible for the breech face marks. And it was thought that marks produced from the same pistol slide, from consecutively manufactured pistol slides, might be similar enough that you would confuse the pistol slides. Basically, it would be very difficult to attribute the marks to a particular slide as opposed to the next consecutively manufactured one. So there were a few studies that tried to investigate this. So I'll talk about the other studies later on when I explain the results. So in this database, there's both 2D and 3D data of the same cartridge case, and this is great because we are then able to compare the results for the two. So this is a summary of the differences between 2D and 3D data. So for the 2D images, these are in PNG format, and so basically we can think of it as a matrix of pixel values where each entry of the matrix is a value between 0 to 255. So the values are on a 256 grayscale. So 0 is black and 255 is white, and the scale in between is linear. For the 3D data, these are in X3P format, and instead of these grayscale values, we have depth values in microns. So like the example that I have up here is 0 to 250 microns, and that's a fairly typical range of values we would get. So X3P just means we have this matrix of depth values, and then we combine it with some metadata in a particular format, and that makes the X3P file. For example, we need information on what type of microscope, what was the magnification, and so forth. So the property measured for 2D data is the reflectance, so how much light is reflected off each part of the cartridge case. For 3D, we're measuring the depth of the surface contours. So how deep is each part of the cartridge case? Then, so for the 2D data, they're all in, they all have the same dimension. It's 1944 by 2592. The width is 2592. For 3D data, so this basically is the size of the matrix that I just talked about. So for 3D data, there's 3 different dimensions. We have something around 2500 by 2500, and then we have 1200 by 1200 and 600 by 600. And the reason that there's these 3 sizes is because they have different lateral resolutions. So the lateral resolution just measures the physical size corresponding to each entry of the matrix. So for the 2D case, each number in the matrix represents an area of 2.53 by 2.53 microns, while for the 3D data, there's 3 different lateral resolutions. We have 1.56, 3.12, and 6.25. So 1.56 would be the highest resolution, and 6.25 is the lowest. These were taken using either different using different magnifications, or the images were downsampled after that. So for example, the 1.56 micron images would be using a magnification of 20x. The 3.12 is a magnification of 10x, or it could be 20x and then downsampled by half. So basically we just take the average of, say, every neighboring pixel. So the final point is that for the 2D data, there's no dropout. So dropouts are missing or NA values. And for the 2D data, we don't have any of those. For the 3D data, there's dropouts. This could be because of the imaging. So how these microscopes work is if the slope is too steep, then it can't get an accurate measurement of the depth at that point, and so it just gives a missing value. So for example, in the ring around the firing pin impression here, the white border, that's actually missing values. Okay, so Now I'll talk about the methodology. Basically, we're interested in coming up with a similarity score. Before that, we have to pre-process the data. So this is just a list of the steps, and I'll go into more detail in a second. So the first step would be to resize to the lowest resolution. So we have 3 different resolutions. We just use the smallest. Then we select the breech face marks. So we want to select the primer area and then cut out the firing pin. Then we level the image and remove circular symmetry. And then we remove outliers and interpolate the missing values, which were the dropouts. And the last step is to filter the image. So then for each pair of images, we answer the 2 questions that I posed earlier. So the first was, we want to know how similar a new image is to the images in the database. For this, we compute a similarity metric. And the similarity metric we're using is a correlation after aligning the images. And then we estimate a measure of the weight of evidence, which was to answer my second question. So we compute a probability of obtaining a higher score by chance. So again, I'm not going to be focusing on this second bullet point. I'm just putting it out there. So now I'll go over the steps in more detail. So the first step was to just to downsample to make everything the same resolution. After we've done that, we want to select the primer region. So the primer region again was the blue outer circle in the plots in the images that I had earlier. To do this, we use a series of image processing steps. So basically, we take the original image, we blur it a little bit using a Gaussian filter, and then we equalize. So we convert it into a binary image. Then we dilate, we fill, we erode, and this gives us the outer circle pretty easily. So the firing pin impression is more challenging. So we would like to do this automatically, but we haven't got it to work as well as we like. So for right now, for this talk, I'm just going to go over results that we've done using a manual selection of the firing pin impression. So basically, I just wrote a tool that lets you select it's like a free-form drawing tool that lets you select the firing pin and cuts it out. So if it's circular, you try and draw a circle. If it's rectangular, you draw a rectangle, and it cuts out everything inside the region that you've marked out. Of course, this is not ideal because it's subjective for one, and it's also not replicable. So we'll be working on getting an automatic method working. So the next step is to level the image, and this is related to Roy, the question that you asked earlier. So if there's a tilt in the way that the person inserted the cartridge case into the microscope, or if just the surface of the primer is somehow tilted, then we correct for this by fitting a model that captures the tilt and then taking the residuals.
How does that work?
How does that work?
Yeah.
So say it's
Well,
tilted.
you're just looking at reflections, right? So how do you know?
Well, these are depth values. So for example, so you would know if it's like, say like this, tilted like this. So you fit a plane like this, and then you take the residuals, and then the remainder the residuals will become horizontal.
Oh, I see. So
Yeah.
it's the depth from some part of the microscope.
Well, it's the depth relative to horizontal. So the microscope so if it's tilted in this way, then these values would look very deep. Well, so yeah, and then these values would be shadow. Yeah. Okay, so I hope you guys heard that. So what we do to level the image is to fit a plane through the surface, so through the depth values, and then take the residuals. So the residuals would be horizontal. So for this particular example, yeah.
Have you ever imaged a cartridge before it was fired?
No.
Well, I'm just wondering about the assumption that it's flat. a plane.
Okay. Yeah.
You should repeat that.
The question was whether I've imaged an unfired cartridge And the answer was no. And the reason for the question was Bill was wondering if, was questioning the assumption that the primer surface is horizontal. Flat. Okay. Okay, anyway, so for this particular example, the surface was actually slightly shallower on the bottom left compared to the top right. So there was a slight tilt on the diagonal. And removing this leads to the residuals on the bottom right here. So the next step is to remove circular symmetry. So this step is similar to the previous step in that it tries to get rid of these global biases. So this one in particular is concerned with circular differences in depth. So the previous one was if it was tilted on a plane, we try to get rid of that. Now, if it's, for example, sloping inwards towards the center, we want to get rid of such effects as well. And the reason why these steps are important is if we have two cartridge cases with the same type of like global topography, so if it's tilted in the same way, for example, then an algorithm might think that the two images are very similar when in fact the individual marks might not be the same. So that's the point of these two steps. So for these circular differences in depth, we can't just fit a simple plane like in the previous steps. So we use a linear combination of circularly symmetric basis functions. So what these are just each basis function contains pixels that are the same distance from the center. So if we use, so the panel up here are the first couple of basis functions, and if we use enough of them, then they're going to cover all of the pixels in the image. So to fit this model, we just take the mean of the depth values for each of the pixels in each basis. So we get the coefficients on the bottom left here. And because there's so many coefficients and the variance is very high, we fit a smoother through these coefficients. So that's the line in red. So for this particular image, there's actually, so you can see that the coefficients are decreasing. So these are enumerated from center outwards. So the coefficients are decreasing, meaning that the depth is actually decreasing from center out, meaning the center is deep and the edges are shallow. So this could be consistent with, for example, the firing pin causing the center area to be depressed. So the fitted model is on the top right, and then again we take the residuals, and this gives us the image on the bottom left. So then we remove outliers, and then we interpolate the missing values. How we interpolate is basically we just take the average of the top, bottom, left, and right values, and then we use a Gaussian filter. So the Gaussian filter highlights certain wavelengths. Well, it lets certain wavelengths through so that some features of the image are highlighted. So in particular, for people who are interested, we use cutoffs of 15 to 150 microns. So after pre-processing, we can compare the two images. So this is an example of two of the original images, and after pre-processing, they look like this. So you can see that there's certain features that are being highlighted. In particular, if you notice, I guess my mouse is not going to work. Okay, so there's a horizontal line on the left part of the image, and if we were to try and match these two images up, you might think that the right image should be rotated slightly, and then you would compute the similarity, the correlation after lining them up. So this is how we do it. So basically we take one image and rotate it repeatedly, and then for each rotation angle we compute the CCF. So CCF stands for cross correlation function. This basically is a correlation for many different translations. So translations here are K and L. And then we do this for multiple rotation angles, and then we store the largest possible correlation that we can get from a pair of images. So this is known as, in the literature, as CCF max. For this particular pair of images, we get the rotation angle to be 12.5 degrees, so meaning that we have to rotate the comparison image 12.5 degrees clockwise, and then that would get the horizontal line that I was talking about earlier to match up. And then this gives us a correlation value of 0.86, which is pretty high. So this is a correlation, meaning it runs from -1 to 1. -1 means it's perfectly negatively correlated, and 1 is perfect positive correlation, and 0 means that there's no relationship between the two images. So here 0.86 is a pretty large value. So for people who have heard my 2D talks, this is just a slide summarizing the differences. So you probably realize that it's very similar. So you can find the work that we've done on 2D. It's coming out in the Journal of Forensic Sciences, and I've also put up the link, and if you're interested, you can look at the code and the explanations. But basically, there's just a couple of minor differences. The first is that for 3D, we had to downsample the data in order to standardize the resolution, but we did not do that for 2D. Right now, so the 2D was completely automatic, so the breech face marks were being selected automatically. But this didn't transfer that well to 3D, which is why we're currently selecting the firing pin impression manually, although we're still working on an automatic solution for 3D as well. We also tweaked the Gaussian filter cutoff slightly. And the final point is that there were dropouts in the 3D data, whereas the 2D data didn't have them, so we interpolated dropouts. So now I'll just talk about the results. So first, I've organized it by the type of study. So this set is for the consecutively manufactured types of studies. So I explained earlier what these meant. So it was basically just consecutively manufactured pistol slides, and the hypothesis was that it might be more difficult to say for sure that that cartridge cases came from one particular slide and not the next consecutively manufactured one, because there might be similar marks between the two. So here there's 4 different studies. So Fadul, Hamby, Lightstone, and Weller. And the labels at the side are the type of firearm and ammunition. So for example, for Fadul, we have a single Ruger firearm. The pistol slide was replaced multiple times with consecutively manufactured slides. And for each slide, there were a couple of test fires using Federal ammunition. So same thing for Lightstone, Hamby, and Weller. And this presentation, these plots here are histograms. So on the horizontal axis, we have the similarity score, and the vertical axis is the density. So I've split the histograms into non-matches and matches. So the non-matches are in red and the matches are in green. So a good result would be if all of the non-matches were had lower scores than the matches. So this would be a good separation. So we're looking for a good separation between the red and the green distributions. So here we see that the results are pretty good. So generally, the algorithm is able to differentiate between pistol slides reasonably well.
What is the word you use? Pistol what?
Pistol slide.
Slide?
Slide. S-L-I-D-E.
Slide.
Yeah.
Okay.
Okay. So next, these are the results from, I call it the same firearm types of studies. So we have 2. Kong on the left used 12 copies of the same Smith & Wesson firearm, and they're using the same ammunition brand. Dekinder on the right uses 10 of the same 10 copies of the same 6-hour firearm, and they fire many different ammunition brands. So we can see here that the results are much poorer compared to what I had on the previous slide. So there might be a couple of explanations for this. For Dekinder, 6 hours don't mark well generally. Also, we know that it's much more difficult to match cartridge cases if the ammunition brand is different as compared to if they were the same. And this is true for examiners. And also we've seen other research done on the Dekinder set, which produced similar results. We sort of have an explanation for why the Dekinder set's performance is so poor. For Kong, I'm not so sure. I couldn't find any other research that was done using the same data set, but I did see somewhere that the Fiocchi ammunition might have manufacturing marks. So what these are marks that were produced during the manufacturing process that might look a lot like breechface marks. So that might confuse both the person and the algorithm. So that's one possible explanation. But if people have any ideas, I would be happy to hear them. So the next set of studies are what I call various. So this could be various firearms or various ammunition brands. So here we have 4 MBIDE and 3 FBI studies. So there's FBI, Glock, Ruger, and Smith & Wesson. Each of the FBI studies use various different firearms that are all of the same brand. So various Glocks, various Rugers, various Smith & Wessons, and they all use Remington ammunition. For the MBIDE study, there's 3 different firearm brands, Ruger, Smith & Wesson, and 6-hour, and they use 4 different ammunition brands. So the results of this set of studies is pretty good, much better than the previous slide, and I would say almost as good as the consecutively manufactured studies. The last type of study is the persistent study. So persistent studies try to investigate if after a large number of test fires from the same gun, do the marks persist or are they still the same? So for example, if we compare, say, the first test fire to the 2000, would they still look the same? So for this Kerry Wong study, they fired the same gun, so it's the same Ruger gun 2,000 times and collected the cartridge cases at regular intervals. So all of the pairs here would be matches. There's no non-matches. But you see that the similarity scores are actually pretty low. So it ranges from 0.2 to 0.6 and the mean is less than 0.4. So again, I don't really have a good explanation for why the results for this set are so poor.
Well, you didn't really study persistency. You could have.
Right. So yeah. So this right plot. This right plot is meant to look at the persistence issue.
But if you really wanted to do it, you could take the left plot and divide it into the first 1,000 and the second 1,000 and have 2 histograms.
Right. So it would be, okay. Yeah, no, I agree. So
You still have a chance of getting a PhD.
Good to know. So the second plot on the right, so we compare the first test fire to the remaining so it's until 2000, but we only have them at intervals of 25, so it's about 90 test fires. We see that there is so if the marks did not persist, then we would see a decline from the first to the 2000. But in this case, it's pretty horizontal. There might be a slight decline. But another observation that we make is that there's a lot of variability from shot to shot, meaning that from shot like 15 to 16, the marks could look pretty different. So this slide is the overall result. So if we just take these 800 plus images as a single, yeah.
Do you know if the firearm was cleaned in between?
I think that it was after, well, I don't know. I don't actually know how often they did it, but I think they did like after, at least after 1,000 or something. I'll have to look it up, yeah. So, so these are the, these are the overall results, meaning we take the 800 images as a single data set and we do all of the pairwise comparisons. So we have over 700,000 comparisons, and we can see, so I plotted the same red and green, and we see that there's an overlap between the distributions. The non-matches are mostly have low values, while the matches have a whole range. So it's anything from like 0.2 to 0.9. So if we were to think of just like having a cutoff to differentiate these two, that might not work so well. So just to summarize what I've said so far, we found that we could differentiate consecutively manufactured pistol slides pretty well. We know that 6 hours don't mark well, and different ammunition brands make it difficult to match cartridge cases, and we did see this especially for the Dekinder data set. There's some studies that have very poor results and we're not really sure why, in particular Kong and Carrie Wong. So if anybody in the audience has any ideas, I would appreciate them. So in the final part of my talk, I'm going to be talking about how the 2D results compare to the 3D results. So I just showed this plot on the right, which was the overall results from 3D. So on the left is the corresponding plot for 2D, and we see that the 3D results overall are better than the 2D results, just looking at these distributions. Instead of looking just at the overall distribution, we're also interested in comparing the specific pairs. So for each pair of cartridge cases, we would have both a 2D score and a 3D score. So we can plot the 2D score on the horizontal axis and the 3D score on the vertical axis. And I've split this into non-matches on the left and matches on the right. So there's a couple of possible ways that this plot can turn out. So for example, if there was a very straightforward relationship between the 2D and the 3D scores, we might see, for example, a linear relationship. So we might see a diagonal line. So of course, this isn't the case. If the 3D results were strictly better than the 2D results, then for the non-matches, we might expect to see a horizontal line that is very low. So meaning whatever the 2D score is, we would get a low 3D score for non-matches. And then for matches, we would see a horizontal line that is very high, meaning whatever the 2D score is, we would get a high value for 3D matches. So again, this isn't the case. So we really have sort of a mixed bag. Generally, we see that if the 2D score is high, it's more likely that the 3D score is going to be high, and this is especially true for the matches, which is good. But for low 2D scores, we get a whole range of 3D scores. So in the left parts of the plot, you can see that there's a whole range of possible 3D score. So say your 2D score is somewhere less than 0.1, your 3D score might still be 0.5. So in the case of non-matches, this would be a poor result, but in the case of matches, this would be a good result. So next, I'll just talk about the results by type of study. So for the consecutively manufactured studies, the 2D results were actually better than the 3D results. So these are the corresponding different distributions, and these were the ones I showed earlier. So this is 3D, 2D, 3D, 2D. So you can see that for the so you can see that for the 2D, there's actually a better separation between the match and the non-match distributions. And to try and see what's going on, we looked at the individual scores. So we found that some of these consecutively manufactured pairs had very low 2D scores for the non-matches, which ended up being high scores, high 3D scores, meaning that this area circled in red on the left plot, some of them were from the consecutively manufactured studies, which is a poor result. So this is just one example. So this comes from the Fadul study. So this pair of images was a non-match, and the 2D score was 0.07, which is very small, but the 3D score ended up being 0.56, which is pretty large. And so these were the original images and what they look like after processing for 2D. So these are the 2D images, and these are the corresponding 3D images. So you can see that for the 3D images, the horizontal marks are highlighted much more compared to in the 2D. So one possibility might be that there were some subclass characteristics due to the consecutively manufactured slides that were captured more in the 3D data compared to the 2D data. So the last set of results that we look at are for what I call the various types of studies. So these are the results from 2D, and these are the corresponding 3D results. So 2D, 3D, and in this case, the 3D results are much better. So the comparison is not entirely fair for all of the studies, in particular the Glock study, because for the 2D processing, we use an automatic selection of the firing pin impression, and this worked much better when the firing pins were circular, while Glock's firing pins are rectangular. So a lot of in this 2D plot, a lot of the Glocks had very poor selection of the breech face marks, and since we did it manually for 3D, that could be one reason why this plot looks so much better. But for the rest of the studies, the automatic selection of the breech face marks actually worked well on 2D. So that's not why we get these much better results for 3D. So again, we pick out one of the examples. This is from the FBI Ruger study, and it's a match. So the 2D score was 0.09, which is pretty low. So that's a poor result. But for 3D, we got a score of 0.66, which is a good result. And we observed the same thing. So these are the 2D processed images, and these are the 3D processed images. And we see again that the horizontal lines are highlighted much more in 3D, and this worked well for this pair of images. So to conclude, we see that methods on 2D can be transferred pretty easily to 3D. We found that computation time was much shorter for the 3D data because we use a lower resolution image. So we were using 6.25 microns, whereas for the 2D, we're using 2.53. So the size of the image and the processing time was much faster for 3D. The overall results, looking just at the histograms, were better for 3D compared to 2D. But if we look at the individual pairs, and I gave several examples, the individual pairs might not necessarily be better. So for future work, I mentioned this a couple of times, we want to make the selection of the breech face impression, the firing pin impression for 3D automatic as well. We also would like to do more work on the pre-processing steps and the order of the steps. The third point is to combine. So it seems like maybe the 2D image, the 2D methods on 2D have some advantages compared to methods on 3D. So we might think about combining the results in some way, and hopefully this would give better performance overall. The next point is to compare 2D images against 3D images. So right now what we're doing is to compare within all of the 2D images and comparing those results to within all of the 3D images. But if in the future systems are moving towards 3D, but we still have a lot of historical data that's in 2D, so we might think about methods that allow us to compare the newer 3D data against 2D images. So that's another thing to look at. And the final point is on low dimensional representation of the images. Right now we're using individual pixel values. So these images are still pretty high dimensional objects, and we might think about summarizing them in some way before doing these comparisons in order to reduce both storage and computation time. So that's it, and I'll take any questions.
Everybody in Iowa didn't.
Wait, let me see. So I think it's Italy, but I didn't take it.
Does anybody have any questions? Can you hear me?
I can hear you.
Oh, okay, goody. No questions? I have one question, shall we?
Okay.
So did you try at all to do the comparison? Oh, hold on. Using the subset of 3D images for which you had high resolution values?
I did it once with, okay, so basically in the step where we rotate the image and compare the and compute the scores, I downsample it further. So I downsampled it by 4, and then I compared it to when I downsampled just by 2. And the results for just by 2 were not much better than by 4. So it seemed to me like using the higher resolution images might not be that much better, and also it took much longer. So I didn't pursue that further, but I could.
Okay, thank you.
Thank you.
Any other questions?
I actually had one question.
Okay.
Go for it.
So the equation used to, I guess, basically integrate the area.
I couldn't hear you. What was it?
So the equations used to get your coefficient.
Okay.
I'm sorry, I'd have to go back and look at it, but you're basically integrating the area of the image to an extent.
Mute myself.
Okay. Can you hear me?
Yes, we can hear you.
Okay, so I guess my question was, is that formula for the coefficient, so that's basically what's being used across all these studies, that's pretty much the standard for how you get to that number, that agreement coefficient?
Okay, yes.
Okay, I was just making sure that that's pretty much, everyone's pretty much agreed upon that.
Oh, okay. Well, so
Or is there room for improvement there? I'm just curious.
No.
I don't know.
So NIST actually has done something else. They're using the CMC congruent matching cells. Yeah. So it kind of builds off this idea of the correlation and then adds some stuff. So you might want to look into that as well. But CCF Max is pretty much the standard like baseline thing that you would do.
Right, but it is evolving. There's other things being done. I guess that was my question. You answered it. Thank you.
Okay, thank you.
Any other questions? If there's no other questions. great presentation. For those of you that would like to listen to it again, we will post the entire presentation on the CSAFE website, www.forensicstats.org, pretty soon. And please join us on March 1st for the discussion on the use of likelihood ratios in court. Thank you very much.
Thanks, Alicia.
I'm supposed to say good night, Mrs. McCarthy.
Well, I'm trying to.